Welcome back, listeners, to another exciting episode of Operating Systems Crashcast. I'm Victor, and today we're diving into the fascinating world of thread scheduling. Sheila, are you ready to unravel this complex topic?
Absolutely, Victor. Thread scheduling is a crucial aspect of modern operating systems, and it's essential for anyone looking to understand how computers manage multiple tasks efficiently. Let's get started.
Great. Before we dive into the details, let's set the stage with some fundamental concepts. Sheila, can you give our listeners a quick overview of what thread scheduling is all about?
Certainly, Victor. Thread scheduling is the process of deciding which thread should run at any given time on a CPU core. It's like a traffic controller managing multiple lanes of vehicles, ensuring that each thread gets its fair share of CPU time. The main goal is to maximize CPU utilization while providing fair access to all threads.
That's a great analogy, Sheila. Now let's talk about one of the key concepts in thread scheduling: contention scope. There are two types: process contention scope, PCS, and system contention scope, SCS. Can you explain the difference?
Absolutely, Victor. Process contention scope, or PCS, refers to competition for CPU time among threads within the same process. It's like siblings competing for their parents' attention. On the other hand, system contention scope, or SCS, involves competition among all threads in the system, regardless of which process they belong to. This is more like a city-wide competition where everyone participates.
Great explanation, Sheila. This brings us to an important distinction: user-level thread scheduling versus kernel-level thread scheduling. Can you elaborate on this?
Certainly, Victor. User-level thread scheduling is managed by the thread library in user space, without kernel involvement. It's fast and allows for application-specific scheduling. However, it can't take advantage of multiple CPUs. Kernel-level thread scheduling, on the other hand, is done by the operating system. It's more complex but can utilize multiple CPUs and provides better system-wide thread management.
Excellent point, Sheila. This difference in scheduling levels leads us to various threading models. Can you walk us through the many-to-one and many-to-many models?
Of course, Victor. The many-to-one model maps many user-level threads to one kernel thread. It's simple and efficient for the OS, but can't exploit multiprocessor systems. The many-to-many model, however, multiplexes many user-level threads to a smaller or equal number of kernel threads. This provides more concurrency and can take advantage of multiple processors.
That's fascinating, Sheila. There's also a hybrid model called the two-level model. How does that work?
The two-level model, Victor, is a combination of the many-to-many and one-to-one models. It allows a user thread to be bound to a kernel thread, providing the flexibility of many-to-many with the added advantage of dedicated kernel threads for certain tasks. It's like having both a general pool of workers and some specialized workers for specific jobs.
That's a great analogy, Sheila. Now let's discuss some of the challenges in thread scheduling. What are some key issues that operating systems need to address?
Well, Victor, one major challenge is balancing responsiveness with overhead. Frequent context switches between threads can improve responsiveness, but also increase system overhead. A context switch, by the way, is when the CPU switches from executing one thread to another. Another issue is priority inversion, where a high-priority thread is indirectly preempted by a lower-priority thread. Operating systems need sophisticated mechanisms to handle these situations.
Those are excellent points, Sheila. How do these challenges and different models impact real-world software development and system administration?
Great question, Victor. For developers, understanding thread scheduling is crucial for writing efficient, responsive applications. They need to choose the right threading model and be aware of potential issues like priority inversion. For system administrators, knowledge of thread scheduling helps in tuning system performance, especially on multi-core systems. They might adjust scheduling parameters or processor affinities to optimize workloads.
That's really insightful, Sheila. As we wrap up, could you summarize the key points we've covered about thread scheduling?
Certainly, Victor. We've discussed contention scope, both process contention and system contention. We explored the differences between user-level and kernel-level thread scheduling and examined various threading models including many-to-one, many-to-many, and the two-level model. We also touched on challenges in thread scheduling like balancing responsiveness with overhead and handling priority inversion. Understanding these concepts is crucial for both software developers and system administrators in creating and managing efficient responsive systems.
Thank you, Sheila, for that excellent summary. And thank you, listeners, for tuning in to another episode of Operating Systems Crashcast. Remember, efficient thread scheduling is key to smooth system operation. Until next time, keep those CPUs busy and your threads running smoothly.